Welcome to our comprehensive MCQ masterclass for electrical engineering students. In this video, we'll explore key concepts from magnetic circuits, AC fundamentals, transformers, motors, and electrical safety. Each topic is broken down into easy-to-understand explanations, supported by multiple-choice questions and their answers. Whether you're preparing for exams or brushing up on basics, this series will help clarify essential principles and boost your confidence. Let's begin by understanding the structure and importance of MCQs in online examinations and how they serve as a powerful tool for learning and assessment. Magnetic circuits are fundamental in electrical engineering. They describe the path followed by magnetic flux, similar to how electric circuits guide current. The region near a magnet where its influence is felt is called the magnetic field. Magnetic lines of force, though imaginary, help visualize how flux moves. These lines are also known as lines of magnetic flux, and their direction indicates how an isolated north pole would travel if placed freely in the field. Understanding these basics sets the stage for deeper concepts like flux density and field strength. Magnetic flux is the total number of lines of force in a magnetic field. It's measured in Weber WB, and flux density is the amount of flux per unit area, denoted by B. The flux density is measured in Weber per square meter WB/m2, also known as Tesla. These measurements help quantify the strength and distribution of magnetic fields and materials. The field strength at a point is defined as the force experienced by a unit north pole placed at that location. These concepts are crucial for analyzing and designing magnetic circuits. Permeability is a key property of materials, describing their ability to carry magnetic flux lines. Materials like iron and steel have high permeability, allowing flux to pass easily. Non-magnetic materials, on the other hand, have low permeability. Absolute permeability is measured in Henry per meter (hm), and relative permeability compares a material's permeability to that of free space. These properties determine how materials respond to magnetic fields and are essential for selecting the right components in electrical devices. Reluctance is the opposition to the flow of magnetic flux in a material, analogous to resistance in electrical circuits. It is directly proportional to the length of the magnetic path and inversely proportional to the cross-sectional area. Reluctance is measured in ampere turns per Weber at /WB. Materials with high reluctance resist the passage of flux, while those with low reluctance allow flux to flow freely. Understanding reluctance helps in designing efficient magnetic circuits and minimizing energy losses. Magnetic circuits share many analogies with electrical circuits. For example, magnetic flux is analogous to electric current, and reluctance corresponds to resistance. The total reluctance in a series magnetic circuit is the sum of individual reluctances, similar to resistors in series. In parallel magnetic circuits, the equivalent reluctance is calculated like parallel resistors. These analogies simplify the analysis and design of magnetic systems, making it easier to apply familiar electrical concepts to magnetic circuits. Faraday's laws explain how electromagnetic induction occurs. The first law states that a change in magnetic flux linkage with a coil induces an electromotive force M. The second law quantifies this, stating that the magnitude of induced EMF is directly proportional to the rate of change of flux linkage. The direction of induced EMF can be determined using Fleming's right-hand rule or Lenz's law, which states that the induced EMF always opposes the cause that produces it. These principles are foundational for understanding generators and transformers. Fleming's right-hand rule helps determine the direction of induced EMF in a conductor moving in a magnetic field. The thumb points in the direction of conductor motion, the first finger in the direction of the magnetic field, and the second finger in the direction of the induced current or EMF. This rule is essential for analyzing the behavior of generators and understanding how mechanical movement translates into electrical energy. Lenz's law states that the induced EMF always opposes the change in flux that causes it. This opposition ensures that energy is conserved and prevents runaway effects in electrical systems. The law is mathematically expressed as E equals N d phi/dt, where the negative sign indicates the opposition. Lenz's law is crucial for understanding the behavior of coils, transformers, and motors, especially during switching and transient events. Induced EMF can be classified as dynamically or statically induced. Dynamically induced EMF occurs when a conductor physically moves in a magnetic field, while statically induced EMF results from a changing magnetic field in a stationary conductor. Both types are fundamental to the operation of generators and transformers. Maximum dynamically induced EMF is given by E equals B times V times L, where B is flux density, V is velocity, and L is length of the conductor. Self-inductance is the property of a coil to oppose changes in current flowing through it, resulting in self-induced EMF. Mutual inductance occurs when a change in current in one coil induces an EMF in another nearby coil. The units of inductance are Henry H, and the value depends on the number of turns, flux linkage, and reluctance. These concepts are vital for understanding transformers, motors, and other electromagnetic devices. Inductance of a coil is directly proportional to the square of the number of turns and the cross-sectional area, and inversely proportional to the length of the magnetic circuit. For example, L equals N2S, where N is the number of turns and S is reluctance. Calculating inductance helps in designing coils and transformers for specific applications, ensuring optimal performance and energy efficiency. Alternating current AC is the backbone of modern electrical systems. AC quantities such as voltage and current change both value and direction with time. Most home appliances operate on AC voltage, which is typically represented by a sine wave. Understanding AC fundamentals is essential for analyzing circuits, designing devices, and troubleshooting electrical systems. Waveform is a graph showing how a quantity changes with time. While AC waveforms can take various shapes, the sine wave is the most preferred due to its smooth and predictable nature. The equation Vt equals Vm sin 2 pi describes the instantaneous voltage, where Vm is the peak value and t is time. Sine waves are fundamental for understanding AC circuit behavior and signal processing. Alternators generate AC voltage based on the principle of electromagnetic induction. The magnitude of induced voltage depends on the position of the rotating coil. The shape of the induced EMF is typically a sine wave, and the instantaneous value at any time is given by Vt. Alternators are widely used in power generation and are essential for supplying electricity to homes and industries. AC cycle consists of one positive and one negative part. The time period is the duration taken to complete one cycle, measured in seconds. Frequency is the number of cycles completed in 1 second, measured in Hz, Hz. Understanding these parameters is crucial for analyzing AC signals and designing circuits that operate efficiently at specific frequencies. Frequency is the number of cycles per second, and amplitude is the maximum value of an AC quantity. The frequency of AC mains voltage is typically 50 Hz, and amplitude is also referred to as peak value. These parameters determine the behavior and effectiveness of AC circuits, influencing everything from appliance operation to signal transmission. Angular velocity relates to how quickly the waveform completes its cycle, measured in radians per second. The relation between angular velocity and frequency is omega equals 2 pi. Peak-to-peak values are often measured using oscilloscopes, providing a clear picture of signal magnitude. Understanding angular velocity helps in analyzing rotating machines and AC signals. RMS, root mean square value of an AC quantity, is its effective value, representing the heat-producing component. For a sine wave, the RMS value is 0.707 times the peak value. The average value is also known as the mean value, and is important for applications like battery chargers and motor control. RMS values are indicated by AC voltmeters and ammeters, while average values are used in DC application. Form factor is the ratio of RMS value to average value, and for a sinusoidal waveform it is 1.11. Peak factor, also known as crest factor, is the ratio of peak value to RMS value, typically 1.414 for sine waves. These factors help in analyzing waveform characteristics and designing circuits for optimal performance. Three-phase AC supply is common in industrial and domestic settings. It consists of three voltages displaced by 120 degrees from each other. The phase sequence is typically RYB, and the vector addition of three-phase voltages at any instant is 0. Star and delta connections are used for different load configurations, affecting voltage and current relationships. In star connections, the neutral point is present and line voltage is square root 3 times the phase voltage. In delta connections, there is no neutral point, and phase voltage equals line voltage. These configurations determine how loads are connected and how voltages and currents are distributed in three-phase systems. Transformers operate on the principle of static electromagnetic induction. They transfer electrical energy between circuits using mutual inductance. The core is usually made of silicon steel, and oil acts as an insulator and coolant. Transformers are classified as core type or shell type, each with unique winding arrangements and magnetic circuits. Induced EMF in a transformer winding is calculated using E equals 4.44 F and Φ, where F is frequency, N is number of turns, and Φ is maximum flux. The voltage ratio, turns ratio, and transformation ratio are key parameters for analyzing transformer performance. Step-up and step-down transformers are used based on the required voltage transformation. Transformer ratings are expressed in kVA, representing apparent power. Losses include copper loss and iron loss, with iron loss further divided into hysteresis and eddy current losses. Copper loss varies with load, while iron loss is constant. Understanding these losses helps in designing efficient transformers and minimizing energy wastage. DC motors convert electrical energy into mechanical energy, while DC generators do the reverse. The prime mover supplies mechanical energy to the generator. In DC motors, field and armature windings are connected to DC supply. The force experienced by a current-carrying conductor in a magnetic field is fundamental to motor operation. Fleming's left-hand rule is used to determine the direction of force on a conductor in a magnetic field. The thumb indicates the direction of force, the first finger the magnetic field, and the second finger the current. This rule is essential for understanding the operation of DC motors and predicting their behavior. ACEMF is the voltage induced in the armature winding of a DC motor opposing the supply voltage. It is expressed as EB equals P phi NZ/60A, where P is number of poles, phi is flux, N is speed, Z is number of conductors, and A is number of parallel paths. BAC-EMF regulates motor speed and protects against excessive current. DC motors are classified as shunt, series, and compound types. Shunt motors have constant flux and are used where speed regulation is important. Series motors produce high torque and are never started on no load due to risk of damage from high speed. Compound motors combine features of both shunt and series, offering versatility for various applications. Compound motors have both series and shunt field windings. In long shunt compound motors, the shunt winding is connected across the series combination of armature and series field winding. In short shunt compound motors, the shunt and armature windings are in parallel, and their combination is in series with the series field winding. These configurations affect performance and application suitability. Cumulative compound motors have field windings wound so that their fluxes add, resulting in higher torque. Differential compound motors have windings wound to oppose each other, reducing overall flux and torque. Understanding these types helps in selecting the right motor for specific tasks, balancing speed, torque, and stability. Special motors include universal, stepper, and permanent magnet (PM) motors. Universal motors operate on both AC and DC supply using series windings. Stepper motors are discrete, providing precise control for robotics, clocks, and printers. PM motors have low power requirements and are used in applications needing efficient, reliable operation. Stepper motors operate as electromagnetic transducers or incremental actuators. Variable reluctance stepper motors offer low cost and fast dynamic response. The step angle is calculated as 360 degrees divided by the product of number of phases and poles. Hybrid stepper motors combine permanent magnet and variable reluctance principles, offering precise control in small step sizes. Electrical safety is critical in all installations. Earth resistance depends on electrode depth, size, and soil temperature. Fuses, MCBs, and ELCBs are used for protection against overload, short circuit, and earth faults. Proper earthing ensures safety against electric shock and fire, keeping non-current carrying parts at zero potential. Fuses break the circuit under fault conditions, while MCBs and MCCBs provide automatic protection. HRC fuses use quartz powder to quench arcs. SFU combines fuse and switch for enhanced safety. MCBs protect against overload, short circuit, and earth faults and do not need replacement after tripping. ELCBs prevent electric shocks by detecting leakage current. Earthing connects the metal frame of appliances to ground, reducing resistance and preventing electric shock. The earth wire is connected to non-current carrying parts, and its cross-sectional area is larger to minimize resistance. Proper earthing keeps potentials at zero and is essential for safety in domestic and industrial installations. For domestic installations, earth resistance should be maintained at 3 to 5 ohms. The minimum current a human can feel is 1 mA, emphasizing the importance of low-resistance earthing. Copper is commonly used for earth continuity conductors, and 3-pin sockets ensure proper earthing for appliances. Protective devices include fuses, MCBs, MCCBs, and ELCBs. Each serves a specific purpose, from breaking circuits during faults to preventing electric shocks. Understanding their operation and proper installation is vital for maintaining electrical safety and preventing accidents in homes and workplaces. Special-purpose diodes such as Zener diodes are used for voltage regulation and protection. Zener diodes are also known as breakdown diodes and play a crucial role in maintaining stable voltage levels in circuits. Understanding their function helps in designing reliable electronic devices. Practicing MCQs is essential for mastering electrical engineering concepts. Each question tests understanding of theory, calculations, and practical applications. Reviewing answers and explanations helps reinforce learning and identify areas needing improvement. Regular practice ensures readiness for exams and real-world problem solving. Effective exam strategies include time management, careful reading of questions, and elimination of incorrect options. Understanding key concepts and formulas enables quick and accurate responses. Practicing with sample questions and reviewing explanations builds confidence and improves performance in online examinations. This video covered essential topics in electrical engineering, including magnetic circuits, AC fundamentals, transformers, motors, and safety devices. Each section provided clear explanations and MCQ practice, helping you build a strong foundation. Reviewing these concepts regularly will enhance your understanding and prepare you for exams and practical applications. Electrical engineering principles are applied in designing circuits, selecting materials, and ensuring safety. Understanding magnetic properties, AC behavior, transformer operation, and motor types enables engineers to create efficient and reliable systems. Safety devices protect users and equipment, making knowledge of these concepts vital for professionals and students alike. To deepen your understanding, explore textbooks, online resources, and practical experiments. Join study groups and participate in discussions to clarify doubts. Regularly solve MCQs and review explanations to reinforce learning. Staying curious and proactive will help you excel in electrical engineering and related fields. Congratulations on completing this MCQ masterclass. Your dedication to learning and practicing key electrical engineering concepts will pay off in exams and your future career. Keep revisiting these topics, stay motivated, and remember that consistent effort leads to mastery. Good luck with your studies and professional journey.